Okay, hi everyone. As Dr. Stein said, my name is Kendall Hill. I will be presenting on the effects of barriers on load distribution in a concrete slab span bridge. So some of the motivation for this research, we are looking at a specific slab span bridge located in Minneapolis in Minnesota. The bridge itself has a state permit restriction on it, and this specific restriction limits trucks that would place a load of 80,000 pounds or more in one of the spans from crossing the bridge. So they have to take a detour, which can be up to 15 miles longer and take up to an hour during heavy traffic times. The Department of Transportation has identified this roadway as a critical trucking corridor. And the bridges themselves the bridge itself isn't scheduled for replacement or improvement. It was constructed in 1964 and widened in 1980. It is a 3-span, continuous span, concrete slab span bridge. You can see in the bottom picture there. The end spans are 23 feet 7 inches, and the mid span is 24 foot 7 inches, and the deck thickness is 11 inches. Our objectives here were to collect field data under a known load, and then develop a 3D finite element model of the bridge, evaluate the bridge's behavior, both from the field data and from the model, and then provide recommendations on how the barriers affect the load distribution or the equivalent width of the bridge. So here's what AASHTO says about equivalent width, which is a number that you need in order to determine the live load distribution factor for a slab span bridge. AASHTO gives a set of equations for multi-lane loading, single lane loading, and those are both for interior strips, and then an equation for exterior strips. And then the AASHTO standard specifications also gives an equation for B effective, which is the tributary width of a single wheel load. You can see off to the right kind of the difference between the equations for E and B effective. E, or equivalent width, takes into account both wheel load, or both wheels in the axle of a truck, while B effective is just the single wheel path. A couple equations from the literature that we selected in order to actually evaluate our field test results and our field test data and our finite element model results were the section modulus method, which essentially breaks the bridge up into a bunch of different widths from which you would collect a single strain data point from a load. And this equation takes into account each of those strains as well as the section modulus of the width of bridge that strain value came from. And it's used to spit out an equivalent width. And then the second method that we looked at is the area method. And what this does is it basically takes the total area under the strain curve and approximates it to a width of a bridge width that would sustain the maximum strain measured in the field test or from the finite element model. And it distributes the load to that width rather than the entire width of the bridge, which is what you would see in if you were to plot the strain across the entire width of the bridge. So our methods, we sampled materials from the bridge deck, used those to develop the finite element model along with the geometry of the bridge that we're looking at. And then we conducted field testing, static tests and dynamic tests, and then analyzed the data and looked specifically at the effects of the barriers. So in the finite element model, we looked at running the model with the barriers included and then without the barriers. And then for the field test, we conducted tests near and away from the barrier to look at how the barrier might influence load test results. So the material properties that we measured, we looked at the compressive strength from the slab as well as the concrete barrier, the modulus of elasticity of the slab, and these were obtained from 1 3/4 inch cores and 4-inch diameter cores from the slab and the barrier. We weren't able to collect a 4-inch diameter core from the concrete barrier, so we weren't able to determine the modulus of elasticity of the barrier, but we do have it for the deck itself. We were a little bit surprised by the compressive strength that we observed in the bridge deck and in the barrier. The design strength for both materials was 4,000 psi, and we saw values of a little over 9,000 and a little over 11,000 psi. However, the modulus of elasticity that we measured from the bridge deck was 3,730 KSI, which actually correlates to a concrete compressive strength of about 4,000 PSI. We also collected 6-inch diameter cores from the bridge deck, and from these we obtained samples of the steel reinforcing, and we conducted yield tests on those and determined the modulus of elasticity as well as the yield strength. And we saw a value of 29,800 KSI for the modulus of elasticity, which is just over the 29,000 KSI expected value or the design value. And then we saw yield strength of 80,400 PSI, which is a little bit over the 60,000 PSI design strength for steel reinforcement. So we took these properties and developed finite element models based on them. First, we developed just a plain elastic model using just the modulus of elasticity that we measured in the field. And then we developed two separate cracked inelastic models using the modulus of elasticity as well as Venturi-Williams properties for nonlinear concrete material properties, including uniaxial and biaxial compressive strength of concrete, as well as isotropic elasticity properties for the steel rebar and multilinear hardening for the steel. In addition to the nonlinear properties, we also simulated 2-inch by 6-inch cracks in one of the models and 24-inch by 6-inch cracks in the other model. And this was just to try and capture what the actual bridge condition is, because in the field there is a significant amount of spalling on the bridge that we looked at, and we wanted to reflect that in some of our computer models. And we used ANSYS 3D to develop these models. So after we developed the models, we went ahead and planned out diagnostic bridge testing. We selected 4 static truck locations that we wanted to obtain results that would 2 positions near the barrier in the east and west spans of the bridge, and then 2 positions at the center of the bridge in each the east and west span. And we collected displacement and strain data from all of these locations. Here's a picture of our instrumentation layout. We had 15 strain gauges and 4 LVDTs placed in the west span of the bridge, as well as 10 LVDTs placed in the east span of the bridge. The reason we had a couple LVDTs in both spans, that was to verify that the bridge was symmetric and behaved symmetrically. And then the strain gauges were obviously for determining the load distribution. And we also used some of the displacement data to see if we could come up with a way to determine load distribution based on displacement rather than strain. And we'll talk a little bit more about that as we go along. As you can see on the left, that's the west span of the bridge that we tested, where we installed the 15 strain gauges as well as 4 LVDTs. And then the right picture is the line of LVDTs in the east span of the bridge. So some of our initial data and results from both the finite element models and the field test. This is strain with a load placed near the barrier. You can see the black line is our field data, and then each of the different colored lines represents a different model, while the dashed lines are that model run without barriers, and the solid lines are the same model with barriers included. And we can see that for the strain near the barrier, the most cracked model, so the nonlinear model with the 24-inch cracks, seems to match the shape the best of the field data. Well, the less cracked and the elastic models are a little bit smoother. They aren't as jagged as the field data seems to be. And then we see the same thing when we look at or compare the field data to the finite element models with a load placed at the center of the bridge width, where the most cracked model seems to match the shape and also the magnitude the best of the field data. One interesting thing to note is that the magnitude of the strain doesn't change significantly when the barriers are included in the model versus when the barriers are excluded from the model at the center of the bridge. However, in the previous slide, there was a pretty significant difference, especially near where the barrier is in the magnitude of strain in models with and without the barriers. So that's our the strain data that we collected. And then for displacement, near the barrier, you can see a very similar situation where the barrier seems to significantly influence the behavior of the bridge, basically at the edge or for an exterior strip. And we can see that the field data, or that we collected from the field tests, kind of falls in between the models that included the barrier and excluded the barrier, which we expected, because we know that the entire cross-sectional properties of the barrier wouldn't exactly influence the bridge to a full extent, but they also do provide some additional stiffness. However, one interesting thing to note is that as you move away from the load in the field test, we actually saw upward displacement in our field data where the displacement actually was positive. So there's some uplift in the structure, and that's something that we didn't observe in any of the computer models. And we suspect that might have something to do with the boundary conditions of the structure. And then field data at the center line, or at the center of the bridge, you can see that our field data actually seems to match one of the elastic models without barriers where the load is placed. However, if you look in the upper left, the field data actually does go to 0, which is a characteristic of the models that include the barriers, whereas the models that don't include the barriers have some net displacement near the edges of the slab. So after we collected all the field data, we went ahead and used the two equations that we discussed earlier to look at the equivalent width of the structure. You can see that using displacement data and the area under the curve method for an exterior strip or near the barrier, the equivalent width actually decreases when you take away the barriers, which makes sense. And this was true for both displacement and strain data. However, if we looked at the center line, using displacement data, we see that the equivalent width actually increases when we take away the barriers using displacement data, while it stayed almost the same for strain in some cases. However, the later examples are with other models show that it's very, very close, or there's little difference between the models with and without the barriers near the center line. Additionally, we can see that the area under the curve method seems to provide the most consistent results, whereas the section modulus method seems to, so the area under the curve provides the most consistent results, whereas the section modulus can have extremely different values depending on how the equation is written and whether or not the barriers are included or excluded in the modeling. So then we took all of these numbers and compared them to the AASHTO equations for equivalent width, and we can see that the equivalent width for a single lane loaded interior strip of the bridge is significantly lower, about 80% lower than the values that we determined from our finite element models and also from our field testing, which shows that the equations are very conservative and result in a very conservative load rating. So we saw that keeping in mind that the equivalent width is proportional to the load rating, the equivalent width increases by 12% for exterior strips in the finite element model when the barriers are included versus excluded. However, it decreases on average by 7% when for interior strips when the barriers are included versus excluded. And then we also see that the code is conservative. The load distribution, or the equivalent width, could increase by 45% going from code to field test data, and then it could increase by 97% for exterior strips going from code to finite element model data, and 86%. It could increase by 86% for interior strips going from the code to the finite element model data. So based on this, the bridge in question, the load rating can be increased, and we can see that the barrier does provide a small increase in load distribution when we're looking at an exterior strip of the bridge. However, for an interior strip, it seems to have either a negative impact or almost negligible impact, and doesn't actually improve the load distribution for interior strips. Thank you. Does anyone have any questions?
Thank you, Kendall. Very interesting presentation. So, okay, there's one question on the chat. So the question is, which result did you end up using the field results? Did you end up using the field results or the FEM? They're quite different.
Yeah, we ended up using the finite element model results for our final average load distributions. They seem to be, I don't want to say the most reliable, but the most recreatable, because we have the model and we can continue to run it and develop it. Well, with the field test we just did once.
Okay. Okay, now then, thank you, Kendall. I appreciate your presentation.